Namaskar. Very good morning to all of you and welcome to the amazing session of the Sunday Talk. Today's session is very special. Special for two reasons. Number one is today's date. Not today's date, tomorrow's date. Yes, so tomorrow is 14th March. And if you want to write in American way, we write it as 3.14. And it tells or it talks more about a special number called pi. So yes, tomorrow is Pi Day and we thought that let's make this Sunday session really special by celebrating Maths Day as also Pi Day, and also the second very important thing is it is followed by very important date, that is 8th March, which was International Women's Day. So why not celebrate women in mathematics and also celebrate Pi Day together? So we are here today to have a Pi talk with women in mathematics. The first talk actually is very interesting because it talks about the historical background of pi and also how pi we can find out in our daily life. And it is going to be given by Dr. Supriya Pisolkar, who is an associate professor here in IISER Pune. She is working in the area of number theory and she is going to discuss with us how pi is so important and how this pi came into existence, the historical background of pi. So over to you, Supriya.
Thanks a lot, Shanti, for this kind introduction, and I welcome all of you again here on this session. So let's begin our journey about pi. All of you know what pi is, right? I mean, it is a edible dessert, usually circular in shape. There will be some delicious sweet stuffing inside it, typically made up of apples, and it will be covered by some big crust, right? After looking at this picture, I'm pretty sure that you feel like eating it immediately, right? But I'm sorry. This is not the pie that we are going to talk about. The pi that we are going to talk about is going to be the mathematical constant pi. Okay, I am extremely sorry to disappoint all of you. So let's see what this mathematical constant pi is. Actually, this constant is so important that even after it was known to people for last 4,000 years, it is still included in the school textbooks. Don't you think this itself tells us the legacy of pi, correct? So the textbook definition tells us that you take a circle with circumference C and diameter D. You divide this circumference by diameter, you will get some number. This number, whatever it is, you don't know a priori right now what it is because I haven't told you what is circumference and what is the diameter of that circle, right? So whatever this number is, we are going to call it as pi. Now question here is, if I give you two circles of various sizes, then of course their circumference will change, their diameters will change, and of course I will have these two ratios, right? Let's say C1 by D1 and C2 by D2. What is your guess? Will these two ratios be same? So apparently that is the case. So the two ratios that you will get, they are going to be very, very close to each other. But why should you believe such thing, right? Just because I am telling this to you? No. So let's try to work out some experiments. So here we have Muhammad Taqi from Science Activity Center. And now we are going to compute this ratio of circumference by diameter of this glass. Okay. We have wrapped around the thread around the circle, and now we will measure the circumference by measuring the length of this thread. So looks like it's coming up to 21 centimeter. Now let's try to compute the diameter of this circle. This is approximately, I believe, 6.7 centimeters. Now the ratio comes out to be 3.143. Okay. Now see that this circle has smaller size than the previous circle. Again we will repeat the procedure. We are now again computing the length of the thread, which is circumference, and the diameter, which was 5 centimeter. We will do this activity for various sizes of circles. The diameter and the circumference is computed and the ratio is 3.11. As you can see, although these numbers are different, but they are very close to each other. And I actually request all of you to find something in your house which is of circular shape and try to do this activity and try to find out what more you can get. Now let's go through the historical timeline of pi. Okay, and I'm sure we all love knowing history behind such mathematical concepts, right? As I already mentioned you that this pi was already known to people for more than 4,000 years. So we have to go back to the most ancient civilizations, and prominently there were two such who were mathematically very advanced. One of them were Babylonians and another were Egyptians. Apparently in 1900 BC, Egyptians knew how to compute circumference of a circle. But they knew that there is such a constant, and they also knew that that has to be close to 3. So just to give you idea, the era that we are speaking about is the era when humans for the first time started using iron. It was the era when the last mammoth on the earth became extinct. So can you believe that the civilizations were so mathematically advanced at that time? Isn't it mind-blowing? Let me fast forward a little bit, and from 1900 BC, let's come to 200 AD. Okay, so in the 2nd century, there was a legendary mathematician and physicist, and all of you are aware of him, Archimedes. Right? I am sure in your school, some way or the other, you have seen the mathematical contributions and the science contributions given by Archimedes. He proved that this constant pi is actually bounded by 2 numbers. But I have this question. I mean, okay, I have circle, I can measure circumference, I can measure diameter. But I know that there is this ratio. Okay. But how can actually compute what this constant is, right? Because see, sometimes measuring a circular figure or a surface can be very tricky, right? So how can one come to such type of estimate, right? Or approximation, so to speak. So trick here is that we do little bit of cheating. Okay, so what kind of cheating? So instead of using circle, we will use square, or we will use regular polygons of sides more than maybe 5, 6, 7 and so on. And as we go on increasing the number of sides of this regular polygon, you can see that actually that polygon starts taking a shape closer to a circle. Okay. So rather than working with the circle, we will start working with these polygons. Okay. And that's precisely the idea that Archimedes proposed, and that is called as Archimedes method of approximation. So here is the idea. Let's suppose we are given a circle, and we will fit a polygon inside that circle. Similarly, we will take another polygon, but with same number of sides as the inside polygon, but little bigger in size, which will actually cover the circle. Now, as you can see in the first figure here, I have taken polygon with 5 sides, correct? But you can see that the distance between the inner side of the polygon and the circle is more. Okay. Let's try to increase number of sides of this polygon. Okay, you can see that now the distance has reduced. Again, I will increase number of sides of this polygon. Okay, again the distance has further reduced. Correct. So this is the method to actually approximate this circle from outside and from inside. Okay, but what this has to do with our pi? So point is that, as you can see in this figure, that circumference of the circle is actually trapped between perimeters of these two polygons, right? So if I call P1 as perimeter of the inside polygon, C as circumference of the circle, and P2 as perimeter of the outer polygon, then you have this inequality that P1 is less than C is strictly less than P2, correct? Now, what is our constant pi? Our constant pi is nothing but circumference divided by D, correct? So I will divide by D throughout, okay? And then you can see that actually pi is trapped between these two things, P1 by D and P2 by D, correct? So Archimedes was able to determine that this pi is trapped between two such ratios, which were 223 divided by 71 and 22 by 7. So here comes your well-known number 22 by 7. Okay. So as you can see that pi is value of pi is bounded by 22 by 7. Okay. So Archimedes was able to achieve this when he finally reached using the polygon of 96 sides. I am pretty sure that you are already aware of lots of other contributions of Archimedes to science. Okay. In fact, he was a great physicist, astrophysicist. He tried to study motion of the sun, the moon, and the planets. Okay. And of course, I am aware that you all know his famous story of leaping from his bath and running in all those states on the streets, shouting "Eureka, Eureka!" Right? So I don't have to tell you more about it. There is one sad story attached to this. So it is believed that actually the approximation of pi was his last contribution to the science. Okay. It was believed that he was killed by Roman soldiers when his city was invaded by them. And apparently when he got killed, he was actually doing calculations with these circles and pi. Now let's proceed and let's try to see, after Archimedes' contribution to pi, what more we have understood about it. So in between Archimedes' era, which is like a 2nd century and a 4th century, in between there were many Chinese mathematicians who tried to give better and better approximations for pi. Okay. The idea that they used was same, the approximations by polygons, but point is that instead of using circumference, they used area. So you tell me if I explain you some method like this, okay? So concept is now understood. But if I want to write it down, okay, in order to use it again or to explain it to someone, isn't it little awkward that I will keep on telling you take a polygon of this side, that side and so on, right? So is there a better way to explain this thing, okay? And this problem was resolved by efforts of our Indian mathematicians. So at that time there were like 3 mathematical superpowers. I would say China, India and Persia, okay? So as I said, Chinese mathematicians, of course, they contributed to approximation of pi by using area instead of circumference. But the key idea of actually giving another representation of this pi was due to our Indian mathematician Aryabhatta. Okay. He was born in Patliputra, and if you are aware, at that time, people used to write and speak in Sanskrit. So he was the first one who actually gave the notion of place value notation. He told us that any number can be expressed by using just 10 symbols like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's it. Okay. And in fact, he also proved that the value of the number is decided by the place of that number. Of course, he was aware of the concept of 0. I mean, he did not use the symbol 0 that we are using now, but he used a word for explaining that void or that emptiness. So for explaining this place value notation, he wrote a poem in Sanskrit, and that has 121 verses. Okay. He was able to compute pi up to 4 digits, which is 3.2 1415. Okay. Let me also mention you that Aryabhatta was again one of the finest mathematician India has produced. He was also a great astrophysicist. I mean, his sine tables were widely used in calculating distances between planets. His approximation of pi now tells us that if you take the circumference of any circle, then it is slightly above 3 times the diameter of the circle. Okay. So, let's see whether in our real life we can actually verify this. So here we have Sushant from Science Activity Center. We are now trying to compute the diameter of this wheel. For that we have used this pendulum. Now we are measuring the length of this thread, which is the diameter of the wheel. We have marked it on our scale, and on the road we have now made 4-5 such marks. Now we are wrapping the thread around this wheel to measure the circumference of this circle. I am pretty sure what he is doing here with the wheel and the thread. You can do it with even a smaller bangle if you have in your house. Now let's unwrap the thread, which is the correct measure of the circumference. Let's see how many marks it's actually covering. So it's covering 1, 2, 3. So this actually tells us that what Aryabhatta predicted, that circumference is little over 3 times the diameter, is actually absolutely correct. Another key ideas given by Indian mathematician Madhava of Sangamagrama. He was supposed to be the pioneer of Kerala School of Mathematics. Okay, and this school has actually produced a chain of brilliant mathematicians. Okay, so in 14th century, Madhava introduced the idea of representing a function by a series. Okay. Of course, people believe that even Archimedes were aware of series. So let me explain you what series is. Okay. So it is sum of, you take one term, add another term to it, add another term, and you just go on doing that. So it is just the sum of infinitely many terms. Okay. Point is that if I give you such an infinite sum, how will you make sense of it? Okay, because after some words we usually write ... correct? So there are no specific numbers. So how will you calculate this sum, correct? Nevertheless, what you can do is you can always compute the sum of finitely many terms, right? So okay, let's start with taking sum of first 2 numbers, then sum of first 3 numbers, sum of first 4 numbers, and you go on increasing the terms. You can always do the sum of finitely many terms. Okay, and of course you will start getting larger and larger terms in the sum, right? Point is that when the contributions of the terms in the series become smaller and smaller, it is believed that such an infinite series actually is very close to some number. It reaches very close to some number. Okay, and that's exactly what Madhava did. Instead of using the earlier approximation theory, he was the first one to represent pi in terms of a series. In fact, he was the first ever mathematician to write down a function in terms of a series. Okay. So this all happened in the 14th century, but towards the 17th century, his series became very popular with the name Madhava Grigori Leibniz series. Okay. So as you can see on the slide, the form of this series. Okay. Another interpretation that quickly you can draw from this is that pi is equal to 4 times something that is an infinite thing. It tells you that pi never stops, right? It is a thing that you can actually write exactly equal to some number, some finite thing, correct? That's what it is also telling us. Let me also take this opportunity to tell you Madhava was also the first mathematician to compute sine, cosine and tangents of angles. Okay. He was again one of the brilliant mathematicians India had produced. So let me go little ahead and let me catch the same thread. As I said, pi just goes on and on. Okay. People all around the world were crazy about precise computations of the digits appearing in this constant. Okay. You won't believe, there are super giant computers, and people all over the world are trying to compute these digits up to like billions, trillions of the digits. Okay. But I believe that mathematicians are sensible people. They have living to make. Okay. So I think most of the time what they have settled on is if you want to use pi for any applications, considering value of pi up to 16 digits is actually good enough. Okay. So here is just a small thing to bring a smile on your face. There is a small activity which our Science Activity Center team has developed to tell you that this pi is just a infinite string of digits, where you can also observe that digits do not follow any pattern. Okay, they just pop randomly. Okay, here we have Mosumi from Science Activity Center. As I told you that the digits that occur in the representation of pi, they don't follow any pattern, right? They just pop randomly. So here what we have done is that we have fixed one color code for 10 digits. So for example, here you can see 3 is given orange color, 1 is given blue color, 4 is given yellow color. And by looking at the already computed digits of pi, we are going to make this nice string of colors. So by looking at these strings, you can easily see that no color pattern is repeated. Now, here are some formulae that you have already seen in your textbooks, right? Computing circumference area of circle, computing surface area of cone, computing volume of sphere, right? Now, let me explain you some amazing facts about pi, okay? So, as we were going through the historical timeline of pi, in 17th century, there was a Welsh mathematician, William Joule, and he actually first introduced the symbol pi for this constant C over D. Okay, so this symbol pi is not something randomly chosen, but it actually represents the first letter of the Greek word perimetros. Okay, so this is the representation of P in Greek. Okay, and perimetros, of course, means circumference. Okay. Another very amusing fact is that pi is not a rational number. So pi can never be written as ratio of two integers. Okay, so to speak, we say that pi is an irrational number. Okay. Another interesting fact is that pi is a transcendental number. Pi cannot be seen as a root of a polynomial with rational coefficients. Okay, if you haven't seen this word irrational or transcendental numbers, don't be scared. These are nice, amusing facts in mathematics, and I'm pretty sure you will encounter them later in your curriculum. Okay. So, why we celebrate Pi Day on 14th of March? Okay. So, if you closely look at the digits of pi, which is 3.14, something that goes on, right? So, 3.14 can also be associated to the way of writing the date. Okay, so if you write 14th March as 3/14, then it actually represents the first 3 digits of representation of pi. Okay, it is also Albert Einstein's birthday. Another very amusing fact is this pi is very closely related to things or objects in nature, right? For example, if you consider yourself as a bird flying in the sky and you are looking down at the landscape below, okay? Imagine that there is a river which is with lots of bends, that you are looking at. Of course, there are two types of distances you can take into account. One is the actual length of this river. So nowadays, of course, by using GPS and so on, we can easily compute such distances. Another distance is taking the distance between the starting point and the end point of the river, which is a straight path, correct? Now you take the ratio of the actual length of the river divided by this distance of the straight path. Okay, this constant is actually called as seismicity of the river. Okay? And amazing fact is that if you look at this seismicity factor or ratio of all the rivers in the world, then it is observed that this ratio is actually bounded by our constant pi. Okay. Now let's try to see whether we see pi in our everyday life. If I want to summarize applications of pi, then let me just say that pi is everywhere. Okay, it is all the way from understanding science of universe to calculating length of an atom. It is of course everywhere there in engineering, right? From constructing buildings, many other electrical applications. It is of course used in navigations in GPS. But there is a fun fact that I want to tell you about from biology. Okay. So in biological processes, this constant pi, which itself has no pattern, right? But it plays a role in formation of pattern. Okay. So it is scientifically proven that the stripes of zebra have a size and spacing that is encoded by pi, and the same goes for the spots on leopard. In fact, it seems that pi encodes the size and spacing of many patterns, not confined to just the field of biology. Okay, so I have given here the address of the website, which is actually a Biophysics Society website, and which tells you many more applications of pi in biology and also in medicines. Okay, so with this, I would like to stop. So thank you so much for attending this session, and I believe that from this session, many of you have got at least something to take away with you. Maybe it will be about history of pi, or how to compute the value of pi, or how important it is in our daily life. So I believe that now onwards, whenever you will see this constant pi, you will remember this session. So thank you so much.
Thank you, Supriya, for this wonderful session. It was really amazing to see the number pi and why it is called as an irrational number, how the journey of pi actually began, and how today when we see pi in our, and we also calculate pi and we use pi in our daily life. So thank you so much for this wonderful talk. Now, as I promised, today we are also going to celebrate the women in mathematics. So, we are going to have a wonderful talk by Dr. Anisa Chorwadwala, who is a faculty member here in Mathematics Department in IISER Pune. And she works in a very interesting field of mathematics research, that is shape optimization. And today's this shape optimization theory is what she's going to bring here for all of you. And with this, she's going to discuss how women in mathematics played a very crucial role in discovering various facts about mathematics and making mathematics really important with different perspectives. So over to you, Anisa.
Thank you, Shanti, for the introduction, and I thank the Science Activity Center for giving me this opportunity to talk about women in mathematics. I mean, my presentation will mainly be focused around how even when women were not formally seen in mathematics, they were always there in mathematics behind the scene. So that is the content. Okay, so I will begin with the motivation and the plan of my talk. So the plan of the talk is as follows. So I'll first start with the motivation for the research problem or a problem in mathematics that I'm going to describe in this session. and that particular problem is called as shape optimization problems. And I will also talk at some little more length about a special kind of shape optimization problem known as the isoperimetric problem. And I will talk about its brief history and mainly the story of Quindi, though that's the main focus of my presentation today. And so let's begin. So what we see, mathematicians and even a layman, I mean every human being, what they see around them in nature, nature is enough to make us think and start questions about why are things the way they are. So for example, questions of the following type, it's quite natural to have those questions when we look around, that why are small water droplets and bubbles that float in air approximately spherical, right? Why does a herd of reindeer form a circular patch if they are attacked by wolves? And why does a cat fold her body to form an almost round shape when the cat is left outside on a cold night? Can we hear the shape of a drum? Meaning that if there is a drum playing in the next room, I mean I don't get to see the drum, but I only hear the sound of the drum. So if I have complete information about the sound of the drum, will I be able to guess what shape the drum has? And of all geometric figures having a certain property, which one has the greatest area or volume? And a similar question is, of all figures having a certain property, which one has the least perimeter or surface area? I mean depending upon which dimension your object is placed in. So mathematicians have been trying to answer these questions via what are called as shape optimization problems. So what is shape optimization problem? As the name suggests, a typical problem is to find a shape which is optimal in the sense that it minimizes certain cost functional while satisfying given constraints. So I generally explain this via some optimization problem that we all deal with in our day-to-day life. For example, if I want to buy a TV from the market, and whenever you try to buy something, we tend to bargain. I mean, if not bargain, so then at least we try to find the cheapest one, that will satisfy or that will have all the features that we are looking for in that object. So what I will do, suppose I am buying it from particular website on the internet, then I'm looking for a television. So what I will do search of a television for, say, on Amazon or Flipkart or Snapdeal or whatever your favorite website. And then once I search for all the TVs, I will just sort them in the ascending order of the price. Okay, and then I will look for the cheapest one. The cheapest one need not be unique. There may be many TVs having the same lowest price. Now when I look at the TV, then I realize, oh, this is not the TV that I was looking for. This is like a very outdated, and this is not the one I'm interested in. Then I do some advanced search. Then I will think about the features that I am looking for. For example, if I need a high definition TV, smart TV, if I want Alexa to come with it, and some condition on the diameter of the screen, etc. So I will put all these features and I will do all these filters, and I will again sort them in the ascending order of the price. And now whatever is the cheapest that I get, again it did not be unique, is the TV that I will go and I will buy, because it has all the properties, all the features that I am looking for, and it is the best price that I can buy it for. So that is the optimization problem in a day-to-day life, and similarly we do it in mathematics. So you have some cost in your mind. The cost could be in terms of some geometric properties like perimeter, and also you try to minimize this perimeter, for example, among all the sets which satisfy a given constraint. So the constraint could be like the filter that we had or the features that we had. The constraints could be that all the domains having a particular area like that. So mathematically speaking, what I want to do is I want to find a domain omega that minimizes a cost functional. I will denote this cost functional as j of omega. Okay, it's a function of the set, possibly subject to a constraint of the form g omega equal to 0. So whatever the constraint I have, I will just give it a mathematical form and I will just put it g omega equal to 0. That is, omega satisfies this mathematical condition. So in other words, I am minimizing this j omega over a family f of admissible domain. So whatever TVs that were satisfying the constraints I had, satisfying the features that I expected them to have, will be called admissible TVs. So similarly, the domains which satisfy the constraints, I will call them admissible domains, and I will collect them in a single bag and call that bag as the family F. Okay, so and then among all the domains in this bag that I have collected, I will find the one for which j omega is the lowest, like that. So that is to find a star domain in this family from this bag, such that the cost for this particular domain is the lowest among all the cost in the family. Okay, so now it's time to talk about a particular example of a shape optimization problems, namely the isoperimetric problem. I mean, I shouldn't say the isoperimetric problem. There is one classical isoperimetric problem, but there are so many isoperimetric problems in literature available, and I mean, as I explained it to you, you will realize that isoperimetric problem can be thought of. I mean, the situation that you can imagine that can give rise to an isoperimetric problem, like the day-to-day cost optimization problem, price optimization problem. The moment you change the family, the moment you change your cost functional, you get a new optimization problem. So similarly here also, depending upon whatever whatever you can imagine and you can formulate it mathematically, that gives rise to a new isoperimetric problem. But before you understand this, maybe let me explain to you what I mean by an isoperimetric problem and why is an isoperimetric problem an example of a shape optimization problem. Okay. So what is an isoperimetric problem? So isoperimetric problem is to enclose a given area capital A, which is given to you, it's a fixed positive number, with the shortest possible curve. Okay. So you are given a thread or a chain of gold, and I don't want you to spend I want you to use as little length of the chain, so that the chain, when you place it on a piece of paper, the area enclosed by this chain curve is at least this capital A that I have given you. So you can think of this capital A as, say, 100 square millimeter. Okay, so I am giving you a gold thread, and I am telling you that using this gold thread, you enclose, make a curve. It could be a square, it could be a rectangle, it could be a circle, it could be an ellipse, it could be some amoeba like shape. So make a loop using this gold thread such that the area enclosed by this loop is at least 100 millimeter square. If I pose this question to you, what do you think will be the shape? Which shape will enclose the desired area such that the length of the thread is minimum? And so why is this an example of a shape optimization problem? Because the cost functional over here that we are considering is the perimeter of omega that we want to minimize, because that is, it's expensive, right? It's a gold thread. I mean, I just to like make you understand why minimizing the perimeter could be of interest. And the constraint that we have is g omega is equal to 0. That is, the area of the domain enclosed should be exactly equal to the fixed number. In our case, it was capital A, and in the example that I considered, it was 100 millimeter square. So what the classical isoperimetric theorem says, it says that in the Euclidean plane, that is, if you have a plain paper and you put the gold thread on the plain paper, then the curve which will minimize the perimeter such that it encloses the area capital A, which is fixed a priori, will be a circular shape. And it is a unique solution. No other shape will have exactly will minimize the perimeter. So if it is some curve which is not a circle, then the perimeter will be larger. Okay, so it will not be a perimeter minimizer. And this property of the circle can be expressed in the form of an inequality, which is known as the isoperimetric inequality. And it is important to see this inequality so that you understand the importance of the pi. We are celebrating pi day, so let's celebrate pi in this inequality as well. Okay, so as I was telling you that suppose I am given a thread of given length, that is, the perimeter is constant, then and I want to make a shape, make a loop using this thread and make a shape on this graph paper, any shape that I like. Okay, so self intersection is not allowed, like it cannot cross each other. Figure 8 is not allowed. Multiple crossing is also not allowed. So it should be like a shape like this without any self intersection. And this is the perimeter of the domain, and if you count the number of squares inside this domain, then that is the area enclosed by the domain. This is how we compute the area. So now, since I am fixing the perimeter, whatever shape that I make with this thread only, and if I want to enclose maximum area, I want to find a shape such that the area is maximum. Then which shape will that be? So this is called an isoperimetric problem because the perimeter is fixed and I want to maximize the area enclosed by the domain. Similarly, when I have suppose the area is fixed. I am now explaining you the iso area problem where the area is fixed and I have a thread of an arbitrarily large length as I want. So there is no limitation on the length of the thread. I can take it as short as large. I mean, assume that this has infinite length thread over here, a rope over here. So now I want to enclose, say for example, capital A, which is fixed, which you can think of it as 100 millimeter squares, and I want to find the shortest possible length. This is a gold thread. Assume that this is a gold thread. I cannot spend as much as I wish. I want to minimize on the cost. So I want to enclose 100 square meter. So for example, suppose this is 100 square meter, suppose. Then I want to enclose the same area using the shortest possible curve. And this problem will be referred to as iso area problem. And as I explained using that inequality, that solving an iso area problem is equivalent to solving an isoperimetric problem because of the inequality and because when you fix one, you get an upper bound for the other one which is attained when it is a circle, if and only if it is a circle. And when you fix the other parameter, there is a lower bound for the other parameter, and this lower bound is attained when the inequality becomes an equality, and which is precisely the situation when it is a circle. And I would want you to do this experiment on your graph paper using your thread that you might have at home and try to understand yourself why circle is the solution for both these problems. Okay, please try it yourself. But let me also tell you why the problem is called isoperimetric problem. So iso means the same and perimetric means the perimeter. So it's like you consider all the domains having the same perimeter and you try to study something. But I just now told you that this inequality proves the equivalence of isoperimetric problem and iso area problem. For example, if you fix the perimeter L square, okay, if you fix the perimeter L square, when you fix L, then of course L square is also fixed. When you fix L, then L square by 4 pi is fixed, okay, and A will be less than or equal to L square by 4 pi. So when perimeter is fixed in the isoperimetric problem, A will be maximum when A is exactly equal to L square by 4 pi, okay, and that is when the C is a circle, right? So this says that when the perimeter is constant, then area is bounded above, because with a thread of fixed length, you cannot enclose an arbitrarily larger area domain. The restriction on the perimeter will also give some upper bound on how much area you can enclose with that thread. Okay, so it gives an upper bound on the area, and the upper bound is attained if and only if it's a circle. So the area maximizer. Perimeter is constant, area maximizing. You will see that in many of the important inequalities in mathematics, this pi plays an important role, because in many of the important inequalities, the constant that appears is often the volume of the n ball, or the, in two-dimensional, let me call it the area of a unit ball, and the area of the unit ball is in terms of pi. This we all know, and even your very famous Euler's equation, which is something which a great mathematician said it is so beautiful. All the important inequalities and equalities and identities in mathematics involves many of them. I shouldn't say all of them. Many of them do involve this pi, and this is one example. Okay, so I will go through the attempts that were made to prove the classical isoperimetric problem. So the first proof was believed to be due to Zenodorus. This is his lifetime was from 200 BC to 140 BC, and he wrote. Of course, at that point of time, mathematics was not as evolved as it is in today's date. So his proof of the isoperimetric problem was via a sequence of figures, mathematical figures, which indicated that he is proving this result for polygons. Okay, and it was found in the it was known through the collection by Pappus of Alexandria, and so he proved that among all polygons enclosing a given area, the regular ones have the least possible length. That is, among all rectangles having a fixed area, the square will have the minimum length. This again, I think all the up to 12th standard students can prove this. So try to prove this. If you cannot prove the classical isoperimetric theorem in the greatest generality, try to prove that among you know what is the formula for the area of a rectangle, and you know what is the formula for the area of a square. Then prove that among all the rectangles having enclosing a given area, the square has the least possible length. Okay, and you will see in one of the presentations in today's session, one presentation by Parul, you will see that the regular polygons, as the number of sides of a regular polygon goes to infinity, the regular polygon converges to a circle, and also any smooth curve, piecewise smooth simple closed curve, you can approximate it by a polygon. I mean, it need not be a regular polygon, but you can approximate it by a polygon. So using that standard approximation arguments, one can, having seen the proof for the polygons, one can prove it for an arbitrary piecewise smooth simple closed curve, or in other words rectifiable curves. So since then many proofs, so this is like 200 BC to 140 BC, and since then many proofs have been given, some of them incomplete, although they were all employing interesting and fruitful ideas. So without even trying to be exhaustive, the list of mathematicians, we generally swear by their names, who considered these problems. They include Euler, the Bernoulli brothers, Gauss, Steiner, Weierstrass, Schwarz, Levi, Smith. They all attempted, I mean, I won't say they failed, but all of them made some progress. They employed some interesting ideas. These ideas were useful later for a mathematician to prove this later. So the case of, so let me just quote this interesting quote from the Pappus of Alexandria book. So there it is of course very vague, because mathematics was not as rigorous as it is today. I mean, there was no formal mathematics language at that point of time. So the quote is, I will just read it verbatim: bees then know just this fact, which is useful to them, that the hexagon is greater than the square and the triangle, and will hold more honey for the same expenditure of material in constructing each. But we, the human beings, claiming a greater share in wisdom than the bees, will investigate a somewhat wider problem, namely that of an all equilateral or equiangular plane figures having an equal perimeter. That which has the greatest number of angles is always the greater, and the greatest of them, as the number of angles keep on increasing, I told you that the polygon will converge, regular polygon will be as close to a circle, right? It will tend to a circle, and it will having its perimeter equal to them. So this is just something which was directed towards the isoperimetric problem, and it was interesting that this observation was made. Of course, it's not as precise, and it's not like, it is slightly off the mark, I would say, but still, I mean, the observation is important. I mean, okay, so the case of rectangles was already known to Euclid, which was like around 300 BC, and that's why I told you that even a school student should be able to solve this. Little progress was made by Greek geometers until Simon Laurel and Jacob Steiner proved it in the late 18th century. Like, see, remember that we are talking about this problem from 200 BC, and now in 18th century, right, it was proved. And again, their proof was incomplete. They just proved the uniqueness of the minimizer. This Euler and Steiner, they made some progress, but they of course did not prove the complete problem. But using symmetry argument later, Steiner showed that the minimizer is a circle. So this was the uniqueness part which was settled. But he did not prove the existence of a minimizer. The existence was settled by Adler in the year 1882. So remember, so many great mathematicians attempted this. But a mathematician whom maybe many of you might not even have heard his name, Adler, he proved this in 1882. And this is why, see, I mentioned this history and the challenges that many mathematicians faced, just to highlight that the story of Queen Dido is important, so that you know how challenging something is to prove mathematically rigorously. But the observation and the implementation need not take that long. I mean, this is why I mentioned though I said it's a brief history, I think I did give you some glimpse of it. Okay, so like some detailed glimpse of it. So most histories of the isoperimetric problem begin with its legendary origin in the problem of Queen Dido. I will explain you what I mean by the problem of Queen Dido. So what was her problem? Her problem was to enclose an optimal portion of land using a leather thong, which is made out of a hide of an ox. Okay, so there was this leather, and using this leather of an animal, she wanted to enclose a piece of land such that the area is as large as possible. And why did she landed in this problem? I will tell you the complete story in a while. But then if this optimal portion of land is to be enclosed by some leather thong, then solving it on the Euclidean plane was not enough, because our earth is not flat. We all know that it's a curved surface. So there was a need to solve this isoperimetric problem on curved surfaces. I will not get into the development that is made in the isoperimetric problem for curved surfaces. But this is an important picture from, so Queen Dido lived from this in this era 839 BC to 759 BC. So this is where the legendary origin of isoperimetric problem is believed to start from. Okay, and what happened was there was this kingdom of Tyre, which is I think the modern day Lebanon, where there was this king who had two children. Elisa, the elder girl was Elisa, who is also known as Dido, and the younger one was Pygmalion. And when he died, he had made both his children as their joint heir. But when he died, the people of this kingdom treated only the son as their king, and though he was still a very young child. And so later, Dido or Elisa married her uncle, who was second in power to her brother Pygmalion. So there was rumor said that Dido's husband did have some very huge treasure buried somewhere, and Pygmalion was greedy, and he got his brother-in-law murdered, so in the hope that he will get all the treasure that he is secretly buried somewhere. So Queen Dido knew, was intelligent and clever, so she knew what was happening. So once her husband died, she expressed a desire to her brother that she wants to move to his kingdom. She wants to move with him in the palace, and she requested that he send some people to help her in carrying out the shift from her place to his place. And Pygmalion was of course hoping that she will also bring all the wealth with her. So he sent a few people to her place to help her shift to the new place. But what Queen Dido did was, she was not known as Queen Dido at that point of time. She was only known as Elisa. So she instructed, ordered these men whom her brother had sent to throw all the bags. She had a few bags packed to throw them in the ocean as a final offering to her late husband. And she told the people that these bags contain gold which belong to her husband, and she doesn't want to use them, and she wants to throw them away. And all these people, they of course will follow what the ruler or the people in authority tell them. So they just threw everything in the sea. And later Queen Dido told me that now if we go to Pygmalion wanted all this wealth, and when he comes to know that what we did to the treasure, which was supposedly the treasure, then they will have to face the anger of King Pygmalion, and it will not be in the interest of these men. So then she convinced them to flee the kingdom with her, and so they agreed because they had no other choice. But Queen Dido was clever. She did those bags did not have gold. Those bags only had some sand. So she tricked these people, and then they flee the kingdom. Let me also show you their itinerary. So they started from this Lebanon here. They started from Lebanon, and they on their way they landed on this island called Cyprus, and eventually they reached Tunisia. So Lebanon to Cyprus, and finally they landed in Tunisia. And in Tunisia, when they landed, they told the local, the existing king over there that please give me some piece of land where we can have some temporary refuge before we go on to the next destination. And she told the king that I will only take as much of land as I can enclose with this piece of the animal's leather, animal skin. And the king took her very lightly, and he laughed and he said, "How much? Okay, take it. How much can you take? How much can you enclose with this leather?" And she instructed her men to cut this leather, animal leather, into small narrow strips, and she enclosed a complete nearby hill, a very large hill. And later some local neighboring kings helped her in settlement, and she later established her kingdom over there, and she became the queen of that place. And it is the modern day, it was called Carthage at that point of time. Now in today's time it is known as Tunisia. It is in Tunisia. And the later part of her story was also very inspiring and fascinating. The way she died, it is something similar to the story of Queen Padmavati, Rani Padmavati of Indian stories, but I don't want to glorify self-sacrifice and so on. But I would maybe request you to read her complete story, how she died, etc. So she was so popular among writers because of her self-sacrifice, etc. That and she was a woman leader at that point of time, and we can imagine how rare it was in that ancient time. So what I'm trying to emphasize by telling you the story of Queen Dido, though she was not formally a mathematician, women started appearing in the formal mathematical scene everywhere around the globe much later. But what I'm trying to emphasize here is, but they were always implementing mathematics without knowing that they are implementing mathematics. They were using mathematics. Even in today's time, women do use mathematics in their day-to-day work, be it in their kitchen, be it outside, or whatever work that they take up. I mean, it's not restricted to women, it's for every human being. We all use mathematics without even realizing we are using mathematics. But this was like see, even today isoperimetric problem is known as Dido's problem, and in Africa women are known as Dido's daughters. Like in India, mathematicians or scientists are known as LILAVATI'S daughters. So I will also list a few motivating resources. LILAVATI'S daughters, the women scientists of India. Please, if you get a chance, get a copy of this book and read it. The Secret of the Surface, the mathematical vision of Mariam Mirza Khani. We all know she was the Fields Medal who died a few years ago recently. And the story of Queen Dido, I mean, her story became so famous that it made space in the mythological and the epic poem written by Virgil to find scholarships in general, but mainly for women in academia, and in particular for women in mathematics. Please do go through these sites to get all the scholarships and various opportunities for higher studies for women. And I hope to see at least 50% representation of women in every front in the academic scene. In today's session, I introduced you to a branch of mathematical research called as shape optimization problem, and I also explained to you a particular example of shape optimization, namely the isoperimetric problem. I gave you a glimpse of its history, and I also spoke about its legendary origin via the story of Queen Dido. Okay, thank you.
Thank you, Anisa, for this wonderful talk. We actually came to know about Queen Dido and her contribution to the area of mathematics and to the area which you are studying. This was really fascinating to know how women have contributed in the area of mathematics. Now, let's discuss more about the area and the relevance of pi, because we always see that pi is associated with area of circle. But how this formula came into existence? So we are here to discuss one more very interesting fact about pi. Yes, pi is associated with area of circle. And to find out how this area of circle actually came into existence, we have our research associate, Dr. Parul Gupta, to discuss with us how this pi is very important and how we can find out the area of the circle. So over to you, Parul.
Thank you, Shanti, for the introduction. And today we are going to see how to approximate area of a circle. So let's start. In schools, in classes, we see that area of a circle is pi r square of a circle of radius r. But we never see how do we reach that formula. We only see formula and never the intuition behind it, how it came. So I'm going to explain the intuition behind it and how do we get the area of a circle. So let's start with the polygon. All of us have seen polygons in school, in life. So a regular polygon is a polygon whose all sides and all angles are equal. Here we also see pictures like equilateral triangle, square with 4 sides, and pentagon with 5 sides, and so on. We can increase sides and we get regular polygons. What are the properties? They have all sides have same length and all angles are same. So these are nice shapes. Now the next concept is the center of a polygon, which is very easy to construct. So the center of a polygon is a point which is at equal distance from each vertex. We see here the centers of triangle, quadrilateral, all centers, how to construct. It's very easy. So now we want to make an observation first. So we have an equilateral triangle here. This is the center of the triangle C, and we call this length R. Now I want to calculate the area of the triangle, the big triangle. So we see that okay, there are 3 small triangles in that cover the full triangle. So the area of the triangle is 3 times the area of the smaller triangle, which is, so the base is A, height is R. So this is half AR. This we know, the area of a triangle is half times base times the height. So we see that okay, if I write it in another way, so I can write it as 3A divided by 2R times R square. And what is 3A? 3A is actually the parameter of the triangle. So this is the sum of all 3 sides. So so we see that the area of a triangle is parameter divided by 2R. 2R is this, so R is the distance of C and the middle, C from the middle point of a side. You can take any side, it's the same, because we are in the case of equilateral triangle. So okay, this is a nice observation. What about if I take a square or a bigger polygon? So we see that even if I take a square, if I calculate the area, I can do the same thing. So I can divide the square in 4 little triangles, like the same case as triangle. So with base A and height R. So we have this area of a square is 4 times half AR, and then I can write it again like this, and I can see that area of a square is again perimeter, because now the square has perimeter 4A. So I add all the sides, then I get 4A. So area of square is perimeter divided by 2R times R square. It's the same for the square also. So now we see, okay, I can do this for any polygon with any number of sides. So, okay. So if I have an n polygon, which is like n-gon, with n sides, then I can divide it into n smaller triangles with base A and height R. So the area would be n times half of AR. I can write it as theta r square, where theta is perimeter divided by 2r. This is, and I want to mention here that this is the first definition of pi. So what is pi? Pi is parameter of a circle divided by the diameter. So this is something like pi, some constant, something like pi, and we have chosen the right definition of diameter for n-gon. So it's a nice activity if you don't need any mathematics or anything for that. So if you take a triangle and if you compute theta, you can you take an equilateral triangle, you can just draw on a page and you can compute, measure with a scale the r, and you can compute theta, and you will see that it will approximate 5.2. If you take a square, you will get 4. If you take a pentagon, you will get 3.65. It's decreasing. When I am increasing the number of sides, the theta value of theta is decreasing. So okay, so when I increase n, then we see that polygon is actually looking like a circle. So you can see in this picture that, okay, when I have a triangle, it's very different from a circle. But when I see this, take 100 gon, which has 100 sides, it's approximately a circle. Like, I mean, if I see it from far away, I can't even tell that it's a polygon, not a circle. So it's very close to a circle. So when I increase n, the number of sides of the polygon, then this theta, which was defined as parameter divided by 2 times the radius, is actually pi. This is the definition of pi. So it is tending to pi, and the area of circle is, that is why pi r square. Like, it's not specific to a circle. Even for any n-gon, you have this formula. It's just another constant. For any n-gon, you have another constant instead of pi, which is approximating to pi when you increase the number of sides. Okay, so this was one method to how we get to this formula pi r square for the area. So we have seen today how to obtain the formula for area of a circle, and it is so interesting to derive formulas instead of mugging them up. So I will encourage you all to derive formulas when you see any interesting formula. Happy Pi Day, and thank you so much.
Thank you, Parul, for this wonderful description and also finding out what exactly means to understand what is area of circle. I hope in today's session we have seen how the journey of pi began, how we right now use pi, and how mathematics and women are so closely associated. And we concluded with the area approximation of circle with the help of pi. So this wonderful pi journey is going to be ended with this talk. Thank you so much for attending this session. I hope all of you have enjoyed today's session, and let this celebration of pi not end here but begin from here, and see you soon. Thank you so much.